The procedure we've been using to construct proofs is capable of handling most any valid argument form, but there are some instances where it falls a bit short. And so the last thing we need to do for this module is consider some additional modified proof methods that we have at our disposal and that we can turn to in these kind of situations. In the end, we'll be looking at two such methods, and in this video we're going to start by looking at what are called conditional proofs. Now, conditional proof is a method that starts by assuming the antecedent of a conditional statement on a separate line in the proof, and then proceeds to validly derive the consequent on a separate line as well in the same basic proof. As you'll see, a conditional proof is a technique for building a conditional statement, and it's one that is used in conjunction with the various rules of inference. So let's take a look at an example. In this particular argument, we find that premise 1 simply asserts Q is true. Premise 2 says if P is true, then if Q is true, then R is true. And then our conclusion asserts if P is true, then R is true. So the first step in using a conditional proof is to just set it up as a proof in general. So we want to list our premises, numbering them in order, in this case 1 and 2, and then set our conclusion off to the right. Now, the first thing to notice here is that our conclusion is a conditional statement, and this is ripe picking for using conditional proofs. While in theory the method of conditional proof can be used to derive any line in a proof sequence, in practice it is usually reserved for obtaining lines that are expressed in the form of conditional statements. So the first step here is to assume the antecedent of that conditional statement, which in this case is P. And what we're going to do here is indent the line at line 3. And we do this because we want to show that this line was merely assumed. It was not derived from any other line, and so it was not validly deduced in our proof. And the fact that we're going to assume P is true is going to have to be listed in our justification in precisely that way. We're going to say assumed as a conditional proof, and we will abbreviate this by just writing ACP, which stands for exactly that. All of our proofs up to this point have contained lines that were either given premises or statements derived from previous lines, which in turn were justified by the implication rules or the replacement rules. This procedure and requirement ensured that each line in the derived proof is a valid argument. However, in this example, line 3 has not been proven. We just assumed it. It is therefore an assumption on our part, and it is only justified as an assumption. But what we can do now is look at the consequences of this assumption. You can think of this as essentially asking, if P is indeed true, then what would follow from this? At this point, we're free to use the implication rules and the replacement rules as long as we acknowledge that any derivation that relies on line 3 is a result of this assumption. And what this means is we're going to have to keep indenting any lines that rely on line 3. We'll have to include those in its own individual proof indented from the original. So we can now infer that if Q is true, then R is true by using the rule of modus ponens and taking line 2, which is a premise, and line 3, which is assumed. Those together will indeed lead to that particular conclusion. And once again, using the rules of modus ponens, we can take line 1, which simply asserts Q is true, and line 4, which says if Q is true, then R is true, and then we can derive the conclusion that R must be true. So notice that 4 and 5 here are still indented, and the reason for that is quite simple. 4 and 5 are both inferences that we can derive that depend ultimately on the acceptance of 3. But 3 was only assumed, and so we can only assume 4 and 5 follow if we accept the assumption that P is in fact true. So all of these have to be indented because they are dependent on this assumption. They are not things that have been derived validly by using the rules of inference from things that we assumed are known to be true. And so at this point, we have all the necessary ingredients to complete our conditional proof here. We started out by assuming P was true, which was the antecedent of the conclusion. And from this, we logically derived the claim that R must be true, which was the consequent of this conclusion. And so our next line in the proof is simply going to combine these results. Essentially, it's telling us if P is true, then R must be true. And notice we have now accomplished our goal. If P is true, then R is true has now been proven, and the proof is complete. Line 6 then is this conditional statement, the one we are after, and it has been derived by a sequence of steps from line 3 through line 5. Now there are a couple things to note about how we set up these kind of proofs. The first is, notice the difference in notation for the lines of our proof. If you look at line 4 and line 5, what we find is that we're using commas to tell us what particular terms we're using. But in line 6, what we're now using is a dash. And that dash indicates that the entire conditional proof sequence was used to derive this particular step. And so we end up with 3-5 to say we used 3, 4, and 5 to derive the CP, which is just our conditional proof. Notice too that line 6 here is no longer indented. This is because we've ended our conditional proof sequence, and so we call this now discharged from the conditional proof. And that means it no longer needs to be indented. The conditional proof sequence starts with an assumption, and the final result of the conditional proof sequence is this conditional statement. That is why line 6 must be justified by listing this entire sequence. And of course, what the proof shows is that the conclusion can be validly derived from our original premises. This method can often be used as a way to simplify a proof and reduce the number of steps you might need to use to get to a conclusion. But it's also worth noting that some arguments exist that have conclusions that can only be derived by way of a conditional proof. And here's a pretty straightforward example of the point. Notice in premise 1 it says if P is true, then not Q is true. And the conclusion is if P is true, then P and not Q is true. The first step, of course, is to just set up the proof as we always do by placing the premise on the left-hand side and numbering them, and then putting the conclusion on the right-hand side and separating that by a slash. Notice then our conclusion here is a conditional statement, and the antecedent of that conclusion is P. And so what we can do in order to set up a conditional proof is simply assume P might be true. And so the second line is going to be indented to show that we're dealing with a conditional proof, that this is an assumed term. And then our justification will just be ACP. And of course, notice we can, using line 1 and line 2 and the rule of modus ponens, derive the inference that not Q is true. And of course, using simply the rule of conjunction, we can put 2 and 3 together into an AND claim, P and not Q. And of course, we've done what we're looking for. Notice the first step in our conditional proof is to assume the antecedent, which is P, and our goal is somehow to derive the consequent so that we can put them together into a conditional statement. At this point, we now know that P is true, or if it's true, then we have shown logically that P and not Q must be true, and so we can simply construct from number 2 and number 4 a nice conditional statement, which is exactly what we're looking for. And of course, putting those together, we're using the entire conditional proof, which is lines 2 through 4, and so our justification is simply going to say 2-4 with CP as an abbreviation for conditional proof. And we got our conclusion. That's what we're looking for. And that, of course, shows us that this is a valid argument. In the end, there isn't much more to conditional proofs than this. What we have to look at last here is simply a way in which they get more and more complicated. And here's the point. It's also possible to have conditional proofs within another conditional proof. Now, in order to make sense of this, we're going to use an example that is frankly fairly complicated. And it looks like this. Premise 1 says, if not P, then not Q. Premise 2 says it's either not R, or if not P, then it's either Q or not U. And then our conclusion says, if R, then if U, then P. And so we need to set this up like we always do, listing our premises, place our conclusion to the right-hand side. And if you haven't noticed, I've shrunk the size of the font and lifted everything to the very top. That suggests it's going to be a pretty long proof. Now, the antecedent of the main operator in this conclusion is R, and we can start then our conditional proof by simply assuming R to be true. But before we start to construct this proof, it doesn't hurt to note that the second premise is a disjunctive statement that has not R as its first disjunct. However, if we use material implication on the second premise, then we can derive another conditional statement with R as the antecedent, which will prove very useful in this particular case. Remember that material implication allows you to convert a disjunctive statement into a conditional statement only by negating the first term. So now that we've established line 3 here, we can begin the conditional proof by simply assuming R, which is again the antecedent of the conclusion, and we want to basically list our justification off to the side, ACP, and indent the entire line to remind ourselves that we're dealing with this conditional statement. Now, before we go any further, we might stop and ask, why did we start here? Why did we start with this material implication and not do it later? It's very important to understand that since every line in a conditional proof sequence is based on an assumption, then each and every line in that proof sequence is not valid outside of that assumption. And so as a general rule, it is fairly smart when you plan to use a conditional proof to start by looking to see if you first need to use your rules of implication or replacement rules on any of your premises before you start in with the conditional proof sequence. And so we can begin the conditional proof by simply assuming R is true, and then we place our justification off to the right as simply ACP. Now, working from the assumption made in line 4, we can now derive the claim in line 5 that if not P is true, then either Q or not U is true, and that follows by rules of modus ponens from 3 and 4 put together. Now, at this point, it is probably useful to stop and think about things for a bit, so we can survey what we have to work with and think about where things are supposed to be going. Now remember, the conclusion that we're aiming at here is a conditional statement, and the antecedent of that conditional statement is just R, which we are now assuming in our conditional proof. That is, line 4 now provides the antecedent of our conclusion. But of course, the consequent here happens to be a conditional statement as well, if U then P. And so in the end, we have to find some way to work through this long conditional proof to derive if U then P, so we can put it together with R in order to get this ultimate conclusion we're aiming at. And it seems like there are a number of available options here. And an immediate option for us is that we can try to use a second conditional proof within this original conditional proof, and then we can work from various conditional statements to try to derive some sort of implication. Now, the two most obvious options here are going to be either that we assume U is true, and then we work from that second conditional statement that is the consequent of our conclusion, or we might start with number 5 here, and we want to assume that not P is true to see what we can get from this. So let's think ahead a few steps to see which of these will be a better option. If we start with U, then it turns out we'll probably have to add Q somewhere along the line in order to isolate P out of this. However, if we start with not P, then we can immediately get the statement Q or not U from line 5. Perhaps transposition at this point will come into play, so we can flip things around. And so let's try not P and see how far we can get. And so we set up our second conditional proof within a conditional proof by once again indenting the line. And so we get line 6 indented where we assume not P, which is the antecedent of number 5, that conditional statement. And again, we're going to say we're assuming it, so we simply write ACP next to that line as the beginning of this second conditional proof. And lines 5 and 6 put together using the rules of modus ponens will lead to the conclusion that it's either Q or it is not U. Now our goal in this with line 7 is to dig out the U at some point. And of course we can do that most plausibly by way of a disjunctive syllogism. But to do that we need to somehow deal with Q. And so if we take line 1, which says if not P, then not Q, and we combine that with line 6, which simply says it's not P, we can derive the conclusion that not Q is the case using the rule of modus ponens. And what we get with line 7 and line 8 is simply a disjunctive syllogism. If we negate the first disjunct, which is Q, we can then affirm the second disjunct, which is not U. And so 9 will give us the conclusion that not U must be the case. Now notice we're getting pretty dang close to the consequent of our conclusion. Notice the consequent of the conclusion says if U, then P. And what we can now do is discharge this second claim because we can connect if not P, then not U together in this second conditional proof. And so we can now discharge line 10 from the second conditional proof. And it says essentially if not P is true, which we get in line 6, then not U is true, which we get from line 9. And since this is a conditional proof, we now have the conditional statement we're looking for. But of course, this is going to be justified by using all of those lines from 6 to 9 as a conditional proof. But of course, what we want is actually if U, then P, not the other way around. And so we can now use the rules of transposition to simply swap P and U and drop the negations to get exactly what we're looking for. At this point, notice line 11 gives us the consequent of the conclusion that we're aiming at. And so at this point, we can return to the original conditional proof, which began with line 4. Remember, line 4 says if R is true, we're making an assumption here. And then all the way through the reasoning, we end up with line 11, which says if U, then P. And now we can just connect that into a conditional statement. So line 4 started one conditional proof sequence, but before it was completed, another conditional proof sequence began with line 6. Now note that both lines have now been justified. And what this allows us to do then is combine all of this into a single proof using 4 through 11 as a conditional proof to draw the conclusion that we're after, which is if R, then if U, then P. And this constitutes proof that this is a valid argument. Now, there are a couple points left that need to be mentioned, and then we're pretty much finished with dealing with conditional proofs. The first is that no line that is part of a conditional proof can be used to support anything outside of that particular proof. To return to the example we've been using, what this basically tells us is no line in our sequence between 6 and 9 could be used to support any line subsequent to line 9. And no line in the sequence between 4 and 11 could be used to support any line subsequent to line 11. Lines 4 or 5 could, of course, be used to support any line in sequence 6 through 9, though. And the final point to make is fairly simple. Every conditional proof must be discharged. You cannot end a proof on an indented line. In the end, you should have some sort of conditional statement that you can pull out from the first and last of your entire proof, and then you set that off on a new line that is no longer indented. So that's pretty much what there is in terms of a conditional proof, what you need to know about it. At this point, it just amounts to practice, practice, practice.